Hello everybody, welcome back. Today we're looking at a problem that has to do with probability. Okay, so a loaded die has the probabilities 1 out of 21, 2 out of 21, 3 out of 21, 4 out of 21, 5 out of 21, and 6 out of 21 of showing 1, 2, 3, 4, 5, 6 respectively. Um, so we'll go ahead and start out. The probability of it showing a 1 is equal to 1 out of 21. The probability of it showing a 2 is 2 over 21. The probability of it showing a 3 is 3 out of 21, which is equal to 1/7. The probability of a 4 is equal to 4 out of 21. The probability of a 5 is equal to 5 out of 21, and the probability of a 6 is equal to 6 out of 21. This is just written, I'm just writing it in an easier form here so that we can refer back to it easier for the other parts of the problem. Now this is equal to 2/7, by the way. This looks like a difficult problem just because it's a lot longer, or it has very many more words than most of the problems that we do here. But a problem that has more words is likely to be more practically applicable than a problem that has very few words. When you get into engineering and solving real life problems, those problems may have thousands of pages of words that you need to solve. But those are the problems that need to be solved more so than your 5-word, 5-line problems. So let's take these one at a time. Part A. What is the probability of throwing 2 threes in succession? So if we are throwing, if we are fulfilling this, if we are throwing 2 threes in succession, we need to throw 1 3, and then we need to throw another 3. We need to throw 1 3 and we need to throw a 3 and a 3. And in probability, when you're dealing with ands, you multiply in most cases. So a probability of 2 threes is a probability of a 3 times a probability of a 3. So that's going to be 1 over 49. We know it reduces, it's 1/7 squared. So then we're going to go on to part B. Not so bad. What is the probability of throwing a 4 the first time and not a 4 the second time? So we have an and here. This means that, once again, we are going to be multiplying two things together. When you have a not in probability, that means you're taking 1 minus the probability of whatever comes after that. So we need, that's the probability of, since it's an and, we're multiplying them. Probability of 4 times the probability of not 4, which means everything else, or another way of thinking of that is 1 minus the probability of 4. So that's going to be, the probability of 4 is 4 over 21. 4 over 21 times, that's going to be, the rest of it is 17 over 21. So that is going to be 68 over 441. Unfortunately, this doesn't really help me out so much as to what the actual value is. I see things better in decimal approximations, so I guess we will, just to make it official, approximately equal to 0.1542. So about a sixth, which is not bad chances. Throwing a 4 and then throwing not a 4, it's not all that unlikely to happen. Continuing on with part C. If 2 such dice are thrown, and we know that the sum of the numbers on the faces is greater than or equal to 10, what is the probability that both are 5s? This is kind of a weird problem to kind of parse out. the fact that we're going into this problem knowing that we're going into this probability knowing that we know something. We know that the sum of the numbers on the faces is greater than or equal to 10. That's conditional probability, meaning that there's a situation that's already occurred, or there's something we already know about the result, which ends up influencing what the actual probability of the event in question is. I'm working on a project that involves conditional probability quite a bit, but that's beside the point. So the probability we're actually looking for is probability of, at least this is the way I'm notating it, probability of a 5 and a 5, given that the sum of the two is greater than or equal to 10. This is a notation that we use it's not typically used in the book that I'm getting these problems from, but it's used in a different probability class that I've taken. So what we need to do is we need to find the, well, actually, okay. So first thing we'll note is that every instance of getting a 5 and a 5 is included in the sum of them being greater than or equal to 10. That's easy to tell because this is only one possibility. There's only one possibility of getting a 5 and a 5, and we know that the sum is going to be equal to 10 in that case. So usually you would find the intersection of these two. The intersection of these two is just this. So so what we need to do is we need to find the probability of getting a 5 and a 5. And what we do is we put it over the probability of the given, which is that the sum of the two are greater than or equal to 10. So let's go ahead and find these then. The probability of getting a 5 and a 5 is easy. 5 and a 5. It's basically what we did before. Notice I'm saying and. That means we're multiplying. We're multiplying probability of 5 times probability of 5. Which means, let's see, where is that? 5 over 21, 5 over 21. So that's going to be 25 over 4, 4, 1. What's the probability that the sum is greater than or equal to 10? So let's think about this for a little bit. We're never going to get that the sum is greater than or equal to 10 with a 1, a 2, or a 3 as the first roll, because we don't have any of the higher numbers other than 6. So, but if we roll a 4 on the first die, and we roll a 6 on the second one, then that will fulfill the condition. Similarly, if we roll a 5 and a 5, that'll fulfill the condition. Or if we roll a 5 and a 6, that'll also fulfill the condition. And then if we roll a 6 on the first one, we can roll a 4, a 5, or a 6 to get greater than or equal to 10. Notice that this is not an and situation. This is an or situation. When you're dealing with ors and probability, you need to add the probabilities together in most cases. So let's take a look at this. It'll be 4 times 6 over 21 squared. That's just these two probabilities multiplied together. So this is the probability of a 4 and then a 6, because we're multiplying these two together. And then we need to add the probability of getting a 5 and a 5. This is the actual case that we're interested in. And then the 5 and a 6. Yeah, that's right. 5 and then a 6 also fulfills it. 21 squared. 6 and a 4 will work for that. A 6 and a 5 will work for that. And a 6 and a 6 will also work for that. Okay. So when we add all those up, I'll spare you the arithmetic. This is equal to 169 over 441. Um, so that's the probability that the sum of them is going to be greater than or equal to 10. So then we can just put these back in here. We have 25 over 441 all over 169 over 441. So I'm running out of room over here, so I'll write it again down here. So the probability of 5 given that the sum is greater than or equal to 10. This is going to be equal to the 441s cancel out. That'll usually happen in the case of conditional probability. 25 over 169. And yeah, I have a decimal approximation here. I said approximation. 0.148. So the probability of the 5 happening, given the given this conditional probability, given that the sum is greater than or equal to 10, is much greater than just the probability alone. You can see that we have 25 over 441, and now we have 25 over 169. So really what you're doing in the case of conditional probability is what you're doing is you're taking all of the cases that so you're given the information that you're given a certain piece of information. What you do essentially with the math is you throw out all of the cases that don't fit that criteria or don't agree with that piece of information, and then you scale it back up so that the probability is equal to 1. That's why you divide by that probability. So in this case, there's 441. It's not really possibilities, but you can since they're not all equal probabilities, they're all weighted differently. But you can think of it like 441 possibilities, but 6 of the first one are these, 5 of the first one are those. So it's not like it's a permutation or whatever, but it's a similar sort of idea, where you're taking all of the probability of the of when it doesn't hold and throwing it out and then scaling it back up so that you have a situation where you're always going to choose something from that new smaller subset. So that's why you'll often have it cancel out there, because it's just, it's just that sort of thing. So yeah, that's another one that's about a sixth. Yeah, so if you know that the sum of the rolls are greater than or equal to 10, there's about a 1/6 chance that you actually have a 5 and a 5. Now we're going to start part D. Unfortunately, my computer crashed last time I tried to start part D. So how many times must we throw the die to have a probability greater than 1/2 of getting an ace? An ace in this case is equal to an ace is a 1. Rolling a 1. So the probability of rolling a 1 on one go is 1 over 21. But instead, the way we're going to think about this problem is what's the probability that we don't get a 1, which is 20 out of 21. Because that we can scale much more easily than the rest of it. So the probability of not a 1 is equal to 20 over 21. So how many times must you throw the die to have a probability greater than 1/2 of getting an ace? That's the same as saying, what is the probability, how many times do we have to throw the die to have a probability less than 1/2 of never getting an ace? Do you see how that works? How many times must we throw the die to have a probability less than 1/2 of never getting an ace? So when we have less than 1/2 probability of never getting an ace, we will at that same point have a greater than 1/2 probability of getting an ace. So that's how we're going to work this problem. Um, the probability of not getting a 1, um, in order for this to be the case, the first time we have to not roll a 1, and the next time we have to roll not a 1, and the next time we have to roll not a 1. On to whenever this condition is fulfilled. That means we are multiplying all of them together. So this probability, just to give you an idea, is 0.952 approximately. Well, my computer crashed again. So talk about probability. What's the probability of a computer crash happening twice while I'm trying to record a video? So we'll try to make this as quickly as possible in order to hopefully make it not crash again. So we're taking multiples of 20 over 21, and we want it to be less than a half. So if we do 14 multiples, we end up with something approximately equal to 0.505. And then if we do a 15th multiple, this takes us over the 1/2 edge and ends up with 48.1, approximately equal to 48.1. Not 48.1, 0.481. Okay, so this means that at 15 is where the probability is greater than 1/2. So the answer to D is 15 times. Finally, hopefully we can get this before my computer crashes again. The die is thrown twice. What is the probability that the number on the die is even the first time and greater than 4 the second time? This is not so bad. So we're multiplying two things together. We're multiplying the probability of an even times the probability of something greater than 4. So greater than 4 is 4, 5, 6. Or actually, no, it's 5, 6. And even is 2, 4, 6. So what we do when we multiply the probabilities together, we keep in mind that even is 2 or 4 or 6, so we're adding those probabilities. Greater than 4 is 5 or 6, so we're adding those, but they both need to hold, so we're multiplying those together. So this equals, so we're adding 2 plus 4 plus 6, and this is because the same numbers appear in their probabilities, and then and a 5 or 6. And this is over 21 squared. So this is going to be equal to 132 over 441, which actually reduces a little bit to 44 over 147, which is then approximately equal to 0.2993. So about a third, 30%, something like that. That's not a low probability either. So there you have it. Probability isn't so bad if you break it down. You need to parse the English into math language, and then after that, it's not too difficult. Thank you so much for watching, and I'll see you next time.